The quantum bump, analyzing perturbations in the infinite square well. Welcome, everyone. Have you ever been curious about how perturbations affect quantum systems? I'm sure you've heard of perturbation theory at some point running through physics, and now we actually get to play with what perturbation theory is. And in this problem, I'll take you through the math and the physics behind the delta function bump in the infinite square well and see how to obtain first order corrections. But with this, keep in mind that this is a very easy system to deal with, and these systems get complex fast. So let's take a look at what we have. In problem 7.1, we're given, suppose we put a delta function bump in the center of the infinite square well, modeled by the perturbed Hamiltonian, which is equal to alpha delta centered at a over 2, so the center of the well, where alpha is a constant. In part A, we want to find the first order correction to the allowed energies, and then explain why the energies are not permitted for even values of n. For part B, we want to find the first three non-zero terms in the expansion of the correction to the ground state. Okay? So not only are we supposed to find the correction, we're supposed to find out what the new wave function and energy levels are. So that'll be fun. But why do we care? Well, as highlighted in the textbook if you read it, what we will encounter is this first order perturbation theory is the most used equation. So that's very important to us. The reason being is that the systems we studied previously were ideal systems, and the real world is more complex and has some weird things to deal with than setting up experiments, that we need these perturbations in order to match what we saw in the experimental realm. And we'll see that come into explicit terms with the fine and hyperfine structure of hydrogen. Very cool stuff there. But given the relationship of the delta function to the sine function, with the derivative, what if instead of a delta function, we had a sine function here that elevated part of the square well floor to something higher? Would that change anything in the expectation value? Why or why not? So let's think about that. As always, don't forget that there is a PDF for you to follow along with. Of course, in this video, it's pretty straightforward and simple for this specific context, so we don't have to worry too much there. But just in case you want it for your collection, feel free to access it using the link below. And if you find value in this content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. No account required. So with that, let's dive into this question. All right. So stop number one. The goal here is to find the first order energy correction. We need to find the expectation value of the perturbed Hamiltonian with the unperturbed wave function. That's very important. We want the idealized system to be used in order to find corrections to the now non-idealized system. Okay, and for the record, this comes in with the equation 7.9. So the first order indicated with this superscript, that's very important. That tells us the order. It's not a power here, so let's be aware of notation. And of course, we have for any state n. So this 0 here, again, is for the 0th order or the non-perturbed. Okay, so just be aware, the superscripts in this theory is the order that we're dealing with. And if you remember, the infinite square well solutions were in equation 2.31. So if we're trying to find the expectation value, what we have to do is put it back in the integral with psi star psi with the alpha psi in between. But since this is an all real wave function, we don't really worry. But we can still take the magnitude squared and be on our way. So knowing that we can bring the constants outside, no big deal there. We can deal with that pretty quickly. We have a lovely sine squared there. Normally this would be a pain to deal with, but because we have a lovely delta function inside an integral, we can just use the shifting property, and we see that we just have to evaluate the integrand, the sine squared, at the position of a over 2. And that's what we see put in here for x. And thankfully, by keeping it ambiguous and not having a defined length on A, we see that they cancel out pretty quickly. Okay, so that's nice to see. And then the idea here is to find out, well, what happens for the cases of n? Since n is ranging from 1 to infinity, how does this oscillate? Because we know that sine squared oscillates, we know trig functions oscillate. How do they do that? Well, for even n, that is to say that n equals 2k, where k is an integer. If we plug that form in here, 2k here for n, we see that the 2's cancel, and we just get something that is a factor of k pi. But we know that for any constant multiple of pi, sine equals 0. So 1 pi, 2 pi, 3 pi, negative pi, it doesn't matter. We know sine equals 0. 0 squared gives us 0, and then 2 alpha over a times 0 gives us 0. Pretty easy there. And this holds for all k that are in the z's, the integers. So analytically, we see why the evens give us all zeros, but there's also a graphical reason, which we'll see in the next slide. However, the odds are a little more tricky, and so the form of an odd number is 2k plus 1, again, with k being in the integers. So we can use the sum and difference formula here to validate this. Of course, if we distribute the pi in, we see here that the value of x, change colors, if we're using x here, x is just going to be 2k pi over 2, which is just k pi. And clearly, if that's the case, we just saw that sine of k pi goes to 0. And then y here would be pi over 2. And so sine would also go to 0. Noting here that if that's the case, sine of pi over 2 would go to 1. And cosine of k pi would go to plus or minus 1. And hence what we see here with the plus or minus 1 in the bracket. Of course, if we square that, a plus times a plus gives us plus, and a minus times a minus gives us plus. So we're good to go there. And we see that we just end up with 1. So we end up with 2 alpha over a for all k as an element of the integers. And so being able to kind of use these things, which we've seen before but may not remember in the middle of it, that's very useful for us. That being said, we now have found the first order energy correction, so let's summarize that and find out what the total energies are with these corrections. Alright, so we have successfully implemented finding the first order corrections, but let's tidy it up. We see here that if we have an even number indicated by n in the 2z, another way of writing even, and then n for odd numbers, we see what we get, but these are just the corrections. If we want to find the total energies, we have to add these corrections to the base level energies on the unperturbed system, and that's what we see here. We just get the infinite square wave energies for evens and infinite plus the perturbation, infinite plus the perturbation energies for the odds. And if we graph this function, what we see here is the dashed line here is the wave function. So that's just the sine square root of 2 over a, sine and all the arguments. But when we look at the square of it, we see here that for in the case of n equals 2, which is given, we have n equals 2 here, which is an even number. We see that we have a 0 crossing for the squared function. And so clearly, if that's the case, at the corresponding point of the bump, which has height of alpha, we see that 0 times this alpha position, it doesn't matter. And we can see that this is the case for every even, not too hard there. The link for this is in the PDF. It's a Desmos graph, so it's pretty easy to play with. But nonetheless, we see graphically and analytically why it has to be 0 for evens. So if that doesn't give you happiness and support, then, I guess you just have to move on to part B, which we will do now. All right. So finally, stop number 2 then. we get to find the new wave function. Now, it's important here that we define to what level of the wave function we want because we saw that psi sub n was the wave function for the nth energy state. And we're told specifically that we want ground state, and remember, in the infinite square well, we start at 1. The harmonic oscillator will start at 0, but in the infinite square well, we start at 1. So with that, n equals 1 here is very nice. Uh, but with that, we have to be careful because in equation 7.13, we saw that the summation was so long that it holds that m does not equal n due to dividing by the energies. Now, if you're curious about how these formulas came about, think about power series expansions, comparing coefficients from those coefficients using the fact that wave functions are supposed to be orthonormal, and then you see that the orthogonality would cancel out weird indices that don't match. So with this, we have to take the integral here because it was an expectation value with the perturbation on these wave functions, one with the index m, one with the ground state n equal 1, and then of course the energy corrections, so En minus Em. And then we have to multiply these because these are the coefficients using Fourier's trick onto the base unperturbed base level wave function here. And so all we see here is a whole lot of simplifying to do, which happens really quickly. This square root of 2a can be pushed outside, no big deal. Clearly, we just need to look at the cases where m does not equal 1, since we were given n equals 1. And then we have square roots here in the integral that can be put outside like we did originally. And once we simplify that down, we get to simplify the denominator, pull out that pi squared h bar over 2ma. And then we see here why we can't have m equal 1, because then you'd end up with 1 minus 1 in the denominator. That would lead to a boo-boo. What would also happen is that oftentimes in the numerator that would also cancel to 0, and that's just not going to lead to anything physically constructive. Alright, so with that done, we take all these constants outside. So you see, dividing by a fraction, we multiply by the reciprocal. That cancels a factor of a out from the integral here, a. So we take that out as well. Good to go. Just a lot of bookkeeping here. Thankfully, with this delta function, we simply just need to put a over 2 into the position for x instead of evaluating the integral, and that makes our life very quick. Again, canceling the a's, now we see that we're just in the form of something we dealt with in the last place, where we have sine of pi, sine of m pi, all those kind of things. Let's see how that simplifies. All right, now that we can kind of zoom in a little bit, we see here that all the coefficients or the constants start forming, and we can make it real nice and easy. We're going to play a little game with the square root here, however, so that's why we see a to the 1 power, and we see in the next stop that we square that to put inside the square root to cancel. This will all come into fruition once we simplify the summation, but you'll see that doing that now saves us time later. But nonetheless, what we see here is that we have the integral sign, and then the base sign that was put outside that we can now put all in the numerator. Thankfully, we know that sine of pi over 2 after simplifying from the delta function leads us to 1. So what we're really stuck with is sine of m pi over 2 times sine of m pi over a times x. Okay, but as we just saw, this little fella here goes to 0 for all m that are even. Okay, and since m's restriction was simply not equaling 1, we're supposed to evaluate the summation for 2, 3, 4, 5, 6, 7, and so on until we have the first 3 non-zero terms. With this correction, or rather with this note of sine of m pi over 2 equals 0 for all the evens, we really only have to evaluate at 3, 5, and 7 now, and so that's what we'll focus on to simplify. Alright, so since we're focused in on the odd numbers, we just need the first 3 odd numbers that are not 1. So hence we see a 3 here, a 5, and a 7, and then we can add them all on and so forth and so on. All right, cool. So we know what sine of 3 pi over 2 is. That gives us a negative 1. 1 minus 3 squared is 1 minus 9, so that gives us a negative 8. We see that here. A-okay, we like that. Sine of 5 pi over 2. Well, 1, 2, 3, 4, 5. We get back up to pi over 2. That gives us a positive 1. And then dividing by negative 24, so that's 1 minus 25 is 24. And then similarly here, 7 pi over 2 gives us negative 1. 1 minus 49 gives us 48. Negative signs cancel. We're cool there. We like that. One of the things we can note here is that we have a factor of 8 in this 24 and this 48. And we can write the factor of 8 as 2 over 4 just to simplify calculations. But that leaves us with a 3 and a 6 here. So if you're wondering where that came from, that's because we factored out a factor of 8 from everything. And that'll just make these constants outside a little easier to deal with. And again, we do so just to be able to play games with the square root and simplify down. Noticing that 4 and 4 from the green cancel. And we could put this 2 in a square root by squaring it, which is what we see here. And that gets rid of that 2 and one factor of the 2's from the square. And we see now that we flipped it from 2 over a to a over 2 by manipulating these constants, so it kind of fits together nicely. That being said, we run into the first order of the wave function corrections, so that's pretty cool. And as you see, it kind of looks the same, but now we're expanding this out in sines and cosines, things like that for the infinite square well. And that's why these are approximations. And we can do higher order approximations, but oftentimes what the author and a lot of other papers do is they'll put the first order correction in because that is significant enough up to the significance level of what they're looking for with the amount of decimals that they want, so on and so forth, that doing higher order theory doesn't necessarily lead to anything useful. So first order is generally what we need. Again, this is a very nice example just to get started on the theory, but what we see and what we saw from chapter 3, 4, and a couple places in 6 is that we have degeneracies in the energy spectrum, and that's what we're going to have to focus on next. So keep in mind, nice examples, not always the case of what we actually use though. Alright, so in summary, we saw how to use the first order non-degenerate perturbation theory. Pretty nice intro into the theory. Again, we use the idealized systems to be able to extract approximate results and to really good degree of accuracy for what we're looking at. And oftentimes, this is what we're going to have to use before anything else. So keep that in mind as you're diving into applications and reading papers on quantum mechanics because perturbation theory is the go-to here. Time-dependent perturbation theory, one of the big looming giants, that's going to take a lot to get into, and we won't see that until chapter 11, I believe. So just hang in there, get used to this because you definitely want it and definitely need it. That being said, a massive thank you goes out to my supporters for making this possible. I'm extremely grateful for your support, and if you'd like to see more, you can also become a patron for access to the supplemental material, current and future projects, and of course, one-on-one help. Summertime, it's a little easier to just kind of take a chill pill, relax, but as soon as fall comes and the classes start rolling, that's when the slots are going to fill up. So let us know early and often, and we can find out a plan. And at this rate, we're posting pretty much daily, so you have something every day to start building your library with. That's going to be fun to see what happens in a couple years. Books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. And as always, thank you for watching. Until next time, stay curious.